In this video, we are continuing with our discussion on the solutions of electrostatics, the problems on electrostatics that we were trying. And previously, I had, if you remember, tried up to 20 questions. Of course, they were in bits and pieces because there were similar problems. So I tried a few of them and left a few for you to try yourself. And now we'll be starting from the 21st bit in this segment. And the previous section or the previous 20 questions can be obviously the solutions can be obtained in the previous video on this playlist, in the assignment playlist. So to begin with, we have the first question, that is the 21st one in this case, where we have two charged particles carrying a charge of 2 times of 10 raised to the power minus 8 coulomb to be joined by an insulating string of length 1 meter, and they are placed on a smooth horizontal table. We must find the tension along the string. So that's a straightforward one where we have two charges, and they are separated by an insulating string of 1 meter in length, and the charges being 2 times of 10 raised to the power minus 8 coulomb each. So obviously the electrostatic force of repulsion between these positive charges will be responsible for the tension that acts along the string. So in that case, we just have to find the force, and the force being equal to 9 times of 10 to the power 9, that is the force, the electrostatic force constant multiplied to the charges, that is 2 times of 10 raised to the power minus 8 squared in this case, because both the charges being same, and the distance of separation is 1 meter. So it's very straightforward one. 9 times of 4 is 36, and that will be 10 raised to the power minus 16, and plus 9 makes 10 raised to the power minus 7, and that's in Newton, or we can just take it as 3.6 times of 10 raised to the power minus 6 Newton. That'll be your answer. Moving over to the next bit, which says that we have two identical balls, which each having a charge of 2 times of 10 raised to the power minus 7 coulomb, and the mass of each of them being 100 grams, suspended from a common point by two insulating strings, each of length 50 centimeters long. The balls are held at separation of 5 centimeters apart and then released. So they are held at a separation and then they are released. Now we need to find the electrostatic force on one of the charged balls for that distance, of course, and then secondly the components of the resultant force on it along and perpendicular to the string, okay, and the tension in the string, and finally the acceleration of one of the balls. Now the answers are to be obtained only for the instant just after the release, means the separation being that 5 centimeter separation. Just at that point we need to find the answers that have been asked to obtain. So we'll see what we can do about it. Okay, so we have a support from which, due to some constraint, I'll have to draw the figure onto the left hand side, although I prefer drawing them on the right hand side and answering them on the left hand side, but never mind. So from that common point we have two balls which carry a certain amount of charge. I'll be writing the charge over here. So these are the two balls which are suspended, and they are suspended and left or released from a distance of 5 centimeters. Now this is not the equilibrium position. The equilibrium position will be something different, or maybe this, but we do not know. We need not find that out as well, because the question does not demand us to obtain the equilibrium position. It only says that the balls are released from that point, and the calculation has to be performed from that instant onwards. Now certainly there will be some tension along the string, the tension being equal in that case at that point of time, and the masses of each of those balls is 100 grams. So 100 grams will be 100 times of 10 raised to the power minus 3 kg. The reason I wrote that, because I'll be multiplying the acceleration due to gravity to give its weight, and at that instant there will be an electrostatic force of repulsion on each of them, and the magnitude will obviously be the same, but just for vector sake I'm writing the other one as Fe prime, whereas we know that Fe and Fe prime are equal, but they are just opposite in direction. Each of those balls are 100 grams, but we'll just focus on the left one for the time being. So there will be some resultant. Resultant may not be, well, during the balanced condition in equilibrium, the moment when they achieve equilibrium, that is when the resultant will be equal to the tension. But at this point, when it is released at that 5 centimeter distance separation mark, the resultant may be somewhere else as compared to the line of the tension or the line of the string. So let's say that the resultant at this point of time is acting along that line. So let that be Fr, and we'll have the line of the string somewhere like this. This is the line of the string, if you can see, and we'll be obtaining the angles for sure. But as of now, what dimensions do we have for us? Now this is probably the central line that I can imagine, which is separating these two balls from the center. Let that central point be O, and let this point from which they hang be suspended is the point P, and I name those 2 points where the 2 balls are as A and B. Now we have the naming for making things easier for us. So let's begin with the first one. Now at this instant we need to obtain the force of repulsion between those two. So force acting on either of them will be the same. So what's the force acting? Now it's pretty straightforward once again. The charge on each ball, as we know, is given as how much? Well, if I can recollect, it is 2 times of 10 raised to power minus 7 coulomb. And if we are to consider the force acting between them, then the force will be equal to 9 times of 10 raised to power 9, 2 times of 10 raised to power minus 7 squared over the distance here being 5 centimeters, so 5 times of 10 raised to power 2 to convert it into meters, and that is squared once again. So this is 9, and then we have 4, and then we have 25, while the powers of 10 will be something of the sort 10 raised to power minus 1, if you see that, and then this will be 1.44, then multiplied with 10 raised to power minus 1 is 0.144 Newton. This is what I am getting. You can try yourself. You'll find probably the same answer as well. Now for the second bit that we had, which asked that the components of the resultant force on it along and perpendicular to the string. Now what we must know is that if we are looking for this resultant force is over here, Fr. Now let's first find the resultant force. Now the resultant force will have a magnitude. This is the second bit I'm trying. The resultant force will be having a magnitude. Well, as I see it, this is the force of repulsion, which is 0.144, that squared plus, because the angle between the repulsive force and the weight of the object, which is the other force that is acting on it, that is equal to m times of g. M here is 10 raised to the power minus 1 kg, and g is obviously 9.8. When they are multiplied, we get 0.98, and that is squared again. And so this will be equal to, if you calculate it, it's somewhat coming out to be 0.9905. This is what I'm getting from my calculator. I have calculated it, so I'm afraid you'll have to use a calculator as well, or you can try it yourself completely. But this is what I'm getting right now. And if we are to consider the angle that it makes. Now the angle that a vector makes, a resultant vector, let that vector make an angle, say alpha, with respect to mg. So tan alpha will be equal to, well, the mg can stay alone over here, and that is the cosine component, and so the sine component will be the other one, that is 0.144. It's nearly 1 by 7, but still if we were to calculate it, we'll get alpha to be equal to uh, tangent inverse of that, and if you calculate that out, you will find that this comes out to be nearly equal to uh, probably 8.4, or not 8.4, but somewhere near 8.36 degrees. And what about the angle that this string makes? Let that be theta. Now that string, at that instant of time when they are released from that 5 centimeter mark, that string makes an angle which is tan theta, and tan theta will be equal to, or let's take instead of tan theta, probably I'll have a better one, that is sine theta, because this front distance OA over PA, that's the sine theta for us, and that is equal to 2.5 over 5 over 50, because the length of the string has been provided as 50 centimeters. So now this is 1 over 20, and so theta is now sine of 1 over 20 is 0.05, and that comes out to be nearly equal to 2. What is it? It's I've calculated that it comes out to be approximately 2.86 degrees. Yes. Now what we see is this is 2.86 degrees at that instant of time, and this is making an angle entirely, this one over here, this angle is 8.36 degrees. So that means this vertical line, if I take it as a vertical line, this is making an angle with the string. Now the string over here, this is the angle between the string and the not the vertical line, but the string and the resultant of both the forces. That angle comes out to be the subtraction of these two, that is 8.36 minus 2.86, which is roughly equal to 5.5 degrees. Let me give that to you in another ink so that you can understand or find that angle easily in case you are finding it difficult right now. So this is the angle that we obtain. It's coming out to be 5.5 degrees. So if we are to consider the component of the resultant along the string and perpendicular to the string, so along the string will be cosine of 5.5 degrees, FR cosine of 5.5 degrees. So FR cosine of 5.5 degrees is along the string, and FR sine of 5.5 will be perpendicular to the string. Now FR cosine of 5.5 will be nearly equal to that same FR, because cosine of 0 is 1, so any smaller angle is will be having the value near about that. If you want the value, I'll be giving you the value right now, which is coming out to be nearly 0.986, almost that 9905 that we obtained. That's nearly nearly that value. Now as far as the value of the sine of that thing is concerned, what we can obtain is that 0.9905 times of the sine of that angle, that is sine of 5.5, that will come out to be nearly equal to 0.095 Newton. So this is the value of the resultant along the perpendicular to the string, and this is along the string. So that is what has been asked in the second bit of that question. Now the third bit asks us the tension at that point of time. I have a space over here. I can give you the answer to this question over there itself. Now the tension at this point along the string has to be calculated. But we have already calculated that, because the tension is nothing but the component of the resultant along that line, and that is equal to this value, that is 0.986, because T is equal to, at this instant, will be equal to FR cosine 5.5, and that is exactly the value that we obtained, that is 0.986 Newton. So that has been obtained. And finally we wish to obtain the acceleration now. So this was the third bit, and the fourth bit now is to find the acceleration of either of the given masses. Because the resultant force is 0.9905, and that is equal to the mass times of the acceleration. And what about the acceleration? Well, the acceleration will be equal to that divided by the mass. Mass is 10 raised to the power minus 1, so this is the acceleration. So this is simply 0.9905, but in that case you will have to find the direction as well, because acceleration is a vector quantity. But we have two components of that, so that is more easier to consider when we have the components. So if we are to consider the component along the string, that is along the cosine component, that will be simply equal to that was equal to 0.986, so this will be equal to 0.0986 along the string, and the other one that was coming out to be 0.095. 10 will be multiplied over here. This is wrong. 10 will be multiplied, because 10 raised to the power minus 1 in the denominator. So this is 9.905. My bad. 9.905, and this will be again 9.86 instead of 0.986. Let me write that clearly. So that component will be 9.86 meters per second square. And finally the other one is 0.095, that divided by 0.1 will give me 0.95 meters per second square along the direction perpendicular to that of the string. So these are the values, or these are the solution to that question that we had, pretty different from what we usually observe, because this is not the equilibrium condition that we are always looking for. This is something different. The equilibrium condition, if you calculate it out, what I have calculated, if you calculate it out, then you will find that the equilibrium will be when the angle theta will be nearly 45 degrees. That will be the point of equilibrium, because both the forces will be 0.98. That is when we achieve equilibrium. But that is one thing that you can determine. I leave it to you to try out and find the equilibrium position in this. What would be the equilibrium position in this case? But this is obviously not related to the equilibrium position that we just discussed. In the next bit, however, we have a question related to the equilibrium condition, where we have the 23rd question, where two identical pith balls are charged by rubbing against each other, and they are suspended from a horizontal rod through two strings of length 20 centimeters each, and separation between the suspension points is now 5 centimeters. In equilibrium, the separation between the balls is 3 centimeters. So this is a question related to equilibrium, and the charge on each ball is having a magnitude of 2 times of 10 raised to the power minus 8 coulomb. So in order to approach this is a simple straightforward question related to equilibrium of suspended objects, charged objects. So let's try that. So here we have a rod from which we are suspending two charged objects, and they are rubbed against one another, so obviously they will carry opposite charges. The magnitude of the charges has been provided, so that's not a big deal. So here the distance of separation between them at equilibrium is 3 centimeters, while the suspension points are 5 centimeters apart. So that gives us the distance left over here to be simply 1 centimeters on each side, isn't it? That's just 1 centimeters on each side. The length of the string has been provided to be 20 centimeters. What we wish to determine is the mass on each ball and the tension along the string. So the tension and the mass of each ball, both the balls are identical, and we'll just consider that left one, so that we'll just consider the left one with the equilibrium forces involved. So this is the electrostatic force of attraction in this case, and the distance between the two balls at this point of time is 3 centimeters, and the charge that has been provided, the charge is equal to 2 times of 10 raised to the power minus 8 coulomb in magnitude. Obviously one will be positive, the other one will be negative, as they are attracting one another. Now as far as the equilibrium condition is concerned, we know that let's name the points. So this is O, this is A, and this is B. And what we have from the condition of equilibrium is that the horizontal force divided by the horizontal length, that is AB, which is 1 centimeters, is equal to the vertical force. Now the vertical force is mg in this case, divided by the vertical length, that is OA, and finally we have the slanting force, that is the tension along the string, divided by the slanting length, that is 20 centimeters in that case. Now OA is simply going to be 20 squared minus 1 squared. So it's approximately coming out to be 19.97 to be precise. So this is 20 squared minus 1 squared under root. So that's nearly equal to 19.97 centimeters. You can take it as 20 centimeters. There's no big deal with that. But considering that, we can now obtain the mass that was to be determined, that is equal to the electrostatic force multiplied with the distance OA, which is what we have obtained, 19.97. We can take it to 20, there's no problem with that, but still, and divided by 1. Remember, the centimeter units are going to cancel out, so there's no point multiplying 10 raised to the power minus 2, and that's all, I guess. No, there's 9.8 for the acceleration due to gravity. The electrostatic force at that point is equal to 9 times of 10 raised to the power 9. Charge on each of them is 2 times of 10 raised to the power minus 8 squared, divided by the square of the distance. That point is 9 times of 10 raised to the power minus 4, because it's in centimeters, so that has to be squared as well, converting to meter. And then we have 1, and then we have 9.8, and then finally over here we have 19.97. The 9's get cancelled out. 19.97 doesn't really cancel out with 9.8, so that's actually 19.6 at that point. So if you calculate this, that comes out to be nearly equal to, well, this one is obviously more than 2. This is 2 squared is 4 times of more than 2. That roughly comes out to be 8.2 times of the powers of 10 that we must consider over here is 10 raised to the power minus 7, 10 raised to the power minus 3. So this value gives us nearly 8.2 grams. This is in kgs, of course. So 8.2 grams. Now we wish to determine the tension along the string. Now the tension along the string can be obtained from this formula itself. So we know Fe, Fe is over here, this one. This is Fe, and that over 1 centimeter, so 9 times of 10 raised to the power 9, again 2 times of 10 raised to the power minus 8 squared over 9 times of 10 raised to the power minus 4 times of 1 centimeter and multiplied to 20 centimeters. So 20 is multiplied to this, and that is equal to the value of the tension, and the tension in this case that we obtain is equal to, well, as far as the powers of 10 are concerned, we know that that will be 10 raised to the power minus 3, but that will be again multiplied to 20. So this comes out to be, the 9's get cancelled off, this comes out to be 8 times of 10 raised to the power minus 2 is what I'm getting at this point. So 8 times of 10 raised to the power minus 2 Newton is the tension that acts along the string. So this is the way we try out these equilibrium problems, the equilibrium conditions. I have tried it in the other video as well. You can in the video related to forces for the 11th standard, you can check that as well for the condition of equilibrium. The 24th bit is almost similar to this previous one, so you can try it yourself. I'll leave it to you because there'll be a repetition of process. Obviously the point of suspension is the same, is common over here, as opposed to the previous one where the point of suspension was different, but that was different because they were attracting each other. Here they are repelling each other because they will be having the same charges. So the spheres are identically charged in this case. So, and the separation between the balls is at, well, the question does not end there. It certainly ends at this page. We'll move over to the next page. So at equilibrium, it is found to be 4 centimeters. You need to find the charge on each sphere. That is where it ends, and that is what you have to obtain, and you can obtain that pretty easily considering the condition of equilibrium. In the next bit, we have the 25th question, which says that two identical pith balls, each carrying a charge or charge Q, are suspended from the common point, again the same one, and equal to length L. Find the mass of each ball if the angle between the strings is 2 theta in equilibrium. Again the same thing, so I won't really consider to be bothered about solving that. You can solve it yourself because you can take the help from the previous one that I have tried out, the 23rd one. It was the other way around, of course. The 22nd one was the one, but there was no equilibrium in that case. So next we move over to the 26th one. In case you find it difficult to obtain, you can just comment below and I can help you out with that with another video on that particular problem, or on the particular problems that you might have provided or might have found difficult to try. The 26th one has a particle of charge that is placed directly below at a separation of 10 centimeters from the bob of a simple pendulum at rest. The mass of the bob is 100 grams. What charge should the bob be given so that the string becomes loose? Well, this is something different, but again pretty easy when you consider the electrostatic conditions. So in this case we have over here a particle carrying a charge of 2 times of 10 raised to the power minus 4, 27th or 26th I guess, yes, it was 26. So a particle carries a charge of 2 times of 10 raised to the power minus 4 coulomb and is placed directly below, I do not have space over there, Now I have it. So 2 times of 10 raised to the power minus 4 below a bob of a simple pendulum. So this is the bob of a simple pendulum, and it's tied to a string. The string is above it, obviously, and it is at a distance of 10 centimeters. Now the question is that the mass of the bob being 100 grams, obviously, because now the weight of the bob will be acting in the downward direction. What charge should the bob be given so that the string becomes loose? Now there will be a string tied to the bob, and it will be taut because of the weight of the bob, the weight of the bob being equal to mg over here. And if it is given some positive charge, this positive charge will repel it, and because of the repulsion there will be a point where it will be balancing the weight of the bob, and as a result of that, just beyond that, it will start to loosen it, because the repulsion will take over the weight of the bob, and as a result of that the string will start to loosen. So we just need that minimum condition, the minimum condition being that the force of repulsion has to be equal to the weight. So in that case, these are the typical problems that you come across in electrostatics, where probably the other way around, you are given that you have a certain charge over here, positive or negative, whatever may be, and you have another ball over here whose weight is acting in the downward direction, and in under what condition will it remain balanced. Now obviously this will be provided with a negative charge in that case, and this will be attracted so that the weight is balanced over here. This is, however, the other way around, where the bob is having a weight, and because of that the string is pretty tight. Now you need to loosen it by providing a repulsive force, and the repulsive force is obviously possible when the bob will carry a positive charge. The question is, how much charge must it carry? So the electrostatic force is kq, that the charge that will be possessed by the bob, times of the charge that is present in that at that point below the bob at a distance of 10 centimeters, means 10 raised to the power minus 1 meters, and that is squared, and that is equal to m times of g, m being 0.1 kg, 100 grams, and g is obviously 9.8. So from that we can obtain the charge, which comes out to be 0.1 times of 9.8 times of 0.1 squared, that is this one, and divided by 9 times of 10 raised to the power 9 times of 2 times of 10 raised to the power minus 4, and that gives us the value to be equal to, well, in the above numerator, if you take the powers of 10, you keep the 98 as a whole, and you get 10 raised to the power minus 4 now. This is 9, this is 2, and this is 10 raised to the power 9 and 10 raised to the power minus 4. Well, the minus 4, they do get cancelled out. Then we are left with 98 over 19. 98 over 18. Now 99 over 18 would have given us nearly 5.5. So we keep this to be nearly equal to 5.4, and we take the powers of 10 the other way around, that is 10 raised to the power minus 9 coulomb. So this is approximately 5.4. Even it will be greater than 4 actually, because 98 80 over 18 will give us nearly 4 and then 8, so 4 to be precise, or nearly 4.5. 5.45, you can keep that, so that's 5.45 times of 10 raised to the power minus 9 coulomb. As far as my calculation is concerned, you can try it yourself and find out if there is any different value that you get. Alright, now moving over to the next bit, where we have the 27th one, that is where we have two particles A and B having charges Q and 2Q respectively, and they are placed on a smooth table with a separation D. That's okay. A third charge C is to be clamped on the table in such a way that the particles A and B remain at rest on the table under electrical forces. What should be the charge on C, and where should it be clamped? Okay. Firstly, we'll be considering the condition over here. Now, what has been provided is that we have two charges A and B, and they are carrying the charges Q and 2Q, so both are positive. And the distance of separation between them is D, and they are placed on a smooth horizontal table. That means there is no force of friction, obviously, which would have hindered the or provided hindrance to any kind of repulsive force between them. Now they need to be balanced, so we need to balance them in the first place by placing a third charge, and they have to be balanced obviously electrostatically because the friction is out of question over here. So the electrostatic force, the balancing force for a third charge, now these are the charges A and B. A third charge C will be placed somewhere on that table, on that plane, and let that plane be the sheet that you see, the white sheet that you see on your screen, and it will be somewhere such that it will be balancing. Now, in order that they are balanced, firstly, the force that is acting on them has to be opposed exactly in the opposite direction. Now, if I were to consider the force on the charge B, the force on the charge B, the repulsive force will be along that direction, obviously. And this is the electrostatic force of repulsion. Now, for a third charge C, supposedly you may consider it on the right hand side over here. If you place the charge over there, the point C over there, or the charge C over there, and keep it as positive, it may repel the charge B with the same force, and then you may have the equilibrium condition for B, but certainly not the equilibrium condition for A, because the distances are going to be different, the magnitude is going to be different, so that's not possible in that case. And supposedly you consider the other way around and place the charge C over here, it's still going to have the same problem. It will be balancing the charge A maybe, but it cannot balance the charge B. Same goes with the case of negative charge being placed on either side. So the only possibility that we can consider is at a point between them, and let's say that the charge C is at a point at a distance x from the charge A, and we keep the charge C as a negative because A will be repelled by B and it will be attracted by a similar force by the charge at the point C. And in order for it to be attracted, obviously A being positive, C, the charge at the point C, has to be negative. Same goes with the case of the charge at the point B. If that is being repelled, that has to be attracted by the charge at the point C, and obviously it has to be negative. So these two positions need not be considered. So now we can, having known the magnitude, having known the nature, not the magnitude has to be determined. Having known the nature, now we will be moving over to obtain the magnitude as well as the distance of separation where it must be placed. Now the distance of separation in that case will be equal to, well, the place where the field goes to 0, isn't it? But we'll take it the other way around, because see, A is repelling the charge B with a certain force, so we'll probably balance the charge B. The charge at the point A will be balanced automatically. So the force between A and B is somewhat given by K Q 2Q over D squared. So this is the force between A and B, and that will be balanced by K, and we take this as Q prime. So K Q prime times of 2Q divided by that distance being equal to D minus of X. So this is D minus X whole squared. So what we get from this is the K's get cancelled out, the 2Q's get cancelled out. So we have Q prime over D minus X whole squared, or we can take Q prime over Q to be equal to D minus X whole squared over D squared. Now we still don't have the value of x over here. Similarly, on the similar line, we can consider the force, the balancing force involving the charge q prime and the charge at the point A. And in that case, what we'll obtain, you can check for yourself, that will be q prime over 2q, and that is equal to, well, the distance, as far as the distance is concerned here, the distance will be equal to, well, between them, that is d squared for sure, but for this it will be simply x squared. You can check this condition that we have obtained over here. So what we get by comparing these two conditions, on the left hand side you see q prime over q, and here you see q prime over 2q. That means x squared over d squared is equal to, is half the value of the previous one. So that means by comparison, what we get over here is that uh, d minus x whole squared over d squared is equal to 2 times of x squared over d squared. And that also gives us that d squares can get cancelled out. What that leaves us with is that d minus x whole squared is equal to 2x squared. So we have d minus x to be equal to root 2 times of x, and the x can go to the other side. So we have x times of root 2 plus 1 in that case to be equal to d, or x is equal to d over root 2 plus 1. That is what we get. You can rationalize that and you will find d times of root 2 minus 1 to be equal to the value of x. X is equal to d times of root 2 minus 1 if you rationalize that, because at the denominator you will have 2 minus 1, so that will become 1. So that is the value of x. You put the value of x over there in one of those equations, and what you get is the value of q prime. I will leave it to you to calculate the value of q prime and see what you get. Because the distance was to be obtained, I have obtained that, and the distance related to the charge, that is also provided. From that you can obtain the value of charge. We'll move over to the next question. Now in the 28th bit we have two identically charged particles, and they are fastened to two ends of a spring of spring constant 100 Newton per meter and natural length being 10 centimeters. The system rests on a smooth horizontal table. If the charge on each of these particles is 2 times of 10 raised to the power minus, well, that is a minus 8, yes, minus 8 coulomb, then what you need to find is the extension in the length of the string, of the spring in this case, and we'll assume that the extension is small compared to the natural length, and we'll have to justify the assumption in this case as well. So we have two identically charged particles to be fastened to the ends of a spring whose natural length is 10 centimeters, but it's going to get extended a bit because of the force that is existing between these two charges, the charge on each of them being same, that is 2 times of 10 raised to the power minus 8 coulomb. And that's very simplest of the questions, because the extension is going to be given by force is equal to k times of x, where x is the extension and k is the force constant, which has been provided as 100 Newton per meter, and we just need to find the extension. Now the force that will be between those two charges is for that natural length of 10 centimeters. After that, that will get extended. Now the force for that 10 centimeter, which is 0.1 obviously in terms of meter, and that is squared, and then this is 9 times of 10 raised to the power 9, and multiplied with the two charges, that is 2 times of 10 raised to the power minus 8 squared, and all of that to give us this value of x, that is equal to 9 times of 4, that is 36 times of 10 raised to the power minus, well, that's minus 2 in the denominator, so this is going to be somewhat minus 5, and then the 100 again over there, that is 36 times of 10 raised to the power minus 7, or 3.6 times of 10 raised to the power minus 6 in meters. In terms of centimeters, you'll find it as 3.6 times of 10 raised to the power minus 4 centimeters. Now this is very small as compared to the length, natural length of the spring, obviously, because the charges have very small magnitude, and with that small magnitude you obtain that much amount of force, and the spring constant is pretty high, that is 100. Had the spring constant been very less in decimal values, then obviously that would have helped in obtaining a greater extension, but that is not to be. With a strong spring constant, that is the only reason that we find over here, with a strong spring constant as 100 newtons per meter, that means it will be extended through a meter only due to 100 newtons of force. So that's what we are getting over here. That is the only reason that I find which is causing such small scale of extension. Now this 29th bit, that involves friction. It's not a smooth table, it's on a smooth incline, obviously, not an incline, the upper one, that is 29th. A particle having a certain charge, that's 2 times of 10 raised to the power minus 6, that is 2 microcoulomb of charge, is held fixed on a horizontal table, not a smooth one in this time, and a second charged particle of mass 80 grams stays in equilibrium on the table at a distance of 10 centimeters from the first charge. It obviously stays in equilibrium because it is being restricted by some other force, which is the frictional force, because in the very next sentence we have the coefficient of friction between the table and this second particle is 0.2. So we need to find the range within which the charge of the second particle may lie. It's straightforward. We need to just find the charge, because the force of repulsion here between those two charges is being countered by the force of friction that is acting against the repulsive force provided electrostatically. So for the 29th bit, we have one of the charges as 2 microcoulomb, and the other charge is at a distance of 10 centimeters, and obviously there's a frictional force acting so that it is balancing the repulsive force that is offered by this, and obviously the weight is going to act, and the normal uh, is going to act on it. So F is, as you know, is equal to mu times of the normal reaction force. In this case, usually we denote it as R. I don't know why I have denoted as N, but that's for normal, so that's okay. So mu times of N in this case, and that's balancing the electrostatic force of repulsion over that distance of 10 centimeters. So mu has been provided as 0.2. So we just need to calculate N, as we know, is because of the weight which is acting downward, that is mg, which is equal to, for that mass of 80 grams, 80 times of 10 raised to the power minus 3 in kgs times of 9.8. So K, well, write it directly as 9 times of 10 raised to the power 9 times of 2 micro, that is 2 times of 10 raised to the power minus 6 times of the charge that is carried by this particular fellow over here, divided by the distance, in that case is 0.1 squared, and that is equal to the force that is provided by the frictional force that is opposing the motion, and that is equal to mu times of N. Mu is 0.2. N, as we know, it is 80 times of 10 raised to the power minus 3 times of 9.8. So all of that on one side, and we keep the Q that is to be determined on the other side, and we find the answer. Let me calculate it for you in case you find it difficult. This is 9.8, this is 0.1 squared over, the other terms go down. We have 9, we have 2, we have 10 raised to the power 3 now as a whole, and then we have the value which comes out to be roughly equal to, let me calculate, with all the numbers taken, 2, 8, 98, we have 10 raised to the power minus 6 over here, and then at the bottom we have 9, 2 and 10 raised to the power 3, and what we get is 2's get cancelled out. 8 times of 98 over 9, well, 98 over 9 nearly equal to 11. We'll take it as 11. And as far as this result is concerned, now it becomes pretty easy. 88 times of 10 raised to the power minus 9, we can keep it as minus 8 and take one of those 10s over here, and we keep it to 8.8 times of 10 raised to the power minus 8 coulomb is the charge that I obtain while considering the conditions given as per the question. But what you can also think of is that if the charge is a negative one, it will be attracted by the other charge, but again the force of friction will be acting the other way around. So this value that we have obtained, well, it can be considered as positive or negative, because in both the cases, in one of the cases it is repelled and it is provided by the force of friction as I have shown. The other way around, if you take it, the force of attraction, electrostatic attraction, would have gone the other way around, and the force of friction would have acted the opposite direction, because the force of friction is just an opposing force, and it will be opposing the motion accordingly. So it doesn't really matter whether the charge is positive or negative. If it is positive, it will be repelled, and the force of friction will be acting in that direction. The force of friction will be in the other way if the electrostatic force is attractive in nature. So it's for both the positive and the negative charges. Now for the 30th question, we have a particle carrying a certain charge and certain mass, and that is placed at the bottom of a smooth inclined plane of inclination 30 degrees. Where should another particle be having same charge and mass be placed on the incline so that it may remain in equilibrium? So it's a smooth incline, of course, so no force of friction involved in this case. We can, however, include force of friction, and the question can be in that sense as well. But for your ease, probably the question is in this form, so we'll see what we can do with it. So the 30th question involves an inclined plane, a smooth one, and that is inclined at an angle 30 degree with respect to the horizontal, and there is a ball at the bottom which carries a certain amount of charge. Don't bother about the mass in that case, although it's given 100 grams, but that need not be considered as of now. 2 times of 10 raised to the power minus 6 is what the charge is there on that ball. There will be another ball on that incline of the same mass and same charge, that is 2 times of 10 raised to the power minus 6. But the question is, where should it be placed so that it is going to remain in equilibrium? That means it won't come down. That means it will be balanced. The component of weight acting along that direction will be mg sine 30, and that will obviously be balanced by the electrostatic force of repulsion over that distance that is provided. That is to be obtained, actually, that's not provided. So let's begin with that. So we have 9 times of 10 to the power 9 times of the charge, that is 2 times of 10 raised to the power minus 6 squared, because both the charges are the same, and x squared, which is to be obtained, and that will be equal to the component of the weight that is acting, that is mg sine 30, m being equal to 0.1 kg, 100 grams, g being equal to 9.8. Sine 30, as you know from your very childhood, it's 0.5. So x squared is equal to 9 times of 10 raised to the power 9. We'll keep the square as such because we'll have to obtain the square root of it, as you can see. And here we have, well, 98, and we keep the 0.5, we keep the half of that 0.5, so that it becomes 49 and it's easy to calculate its root, and then 10 raised to the power minus 1, that is 0.1. So this is 49. What happens to, well, let me write it clearly, 49. What happens to this 0.1 is that it can go up, and this can become 10 raised to the power 10 now. Now we can easily calculate the root of this, that is x. This is 3, this is 10 raised to the power 5, this is only 2 times of 10 raised to the power minus 6 now with the square gone, and this is 7. As simple as that. So this is 6 over 7. 6 over 7 is nearly 0.86 if I'm correct, or 0.85 maybe. Yes, 0.86 or 0.85. I'll keep it as 0.86. So 0.86 and 10 raised to the power minus 1 only. 10 raised to the power minus 1 means we have 0.086. And that is going to be the distance in meters, of course. In centimeters it will be 8.6 centimeters. I think I've made a mistake over there with considering that 9.8, but I didn't consider that 10 over there. So there will be a root 10 over here, which will be multiplied to this. And with the value of root 10, as we know, it is somewhere around 3.16. So this is 0.86 times of 3.16. So it's a big number to consider, and 10 raised to the power minus 1 in meters. And so that now becomes equal to, well, 8 times of 3 is 24, but that's going to be greater than that because 0.86 times of 16 has to be considered. So 0.86 times of 16 is roughly about well, 86 times of 16 is 860, plus 86 times of 6 is 516, I guess. 516 and 860 is 13. 1376. 1376, and then you have 86 times of 3 as well, which is half of 86 times of 6. So let's just calculate that. And there I've made my calculation, and I've found that it's coming out to be roughly equal to 27176, and 10 to the power minus 5 in this case. So 0.27176 to be precise in meters, which is 27.17 centimeters. So that's my answer. You can try it yourself and find out what you get, and we'll discuss it. So that's all that I'm going to try in this video. I'll be uploading one more video for the rest of the questions later on, and we'll be doing a whole lot of problems related to electrostatics, very interesting ones. So stay tuned for that. Till then, thank you for watching.